All right, I have a timer because I have 125 slides and we've got 30 minutes. So I've got marks to hit. So stick with me on this. So let's go to the timer. And we are... Oh, let's make sure this works. Yeah, great. Yeah, so this is Postcard, an unreasonably effective tool for machine-to-machine communication. So I'm James. I hang out a lot in the embedded scene. I've been involved in Rust for a while. If you've hung out in any of the embedded rooms or somewhere else, I'm terminally online. So you might have talked to me at some point, or I might have helped you with some problem. But these days I work for my company, One Variable. I do consulting. I do a lot of helping teams either go from one really excited Rust developer to 5 or 10 functional team members, or people who are looking to build their next project and need it right now, or yesterday, if possible. So I do consulting, so if that's the kind of thing you would like help with, feel free to reach out. So I work on embedded systems, which is a totally worthless term that doesn't mean anything, because it's everything from the tiniest system you can imagine to huge things that are all around you. It covers everything, but the way I like to generally describe it is computers you don't necessarily sit in front of. Now, this could be anything from the key fob or the car behind it, or giant expensive scientific equipment like something like this that you would think is maybe digital, but not like a computer or a phone that you sit in front of. They do something specific well, hopefully. Now, one of my most common tasks, either when I get brought in or for the kind of projects that I do myself, is to help computers talk to other computers, which sounds very straightforward, but computers are special little devices sometimes. Sometimes when I get brought in, all the decisions are made. They say, it's wired up like this, it speaks like this, we need optimization, we need something, we need it to work a little differently in some cases. And other times it's a paralyzing void of options, because there might be nothing there, and when they bring you in, it's your job to stare into the void. So I'd like you all to stare into the void of me, of being brought into a brand new project where the entire plan so far is this napkin sketch. You've got a computer talking over USB to a much smaller computer, a microcontroller unit, something itty bitty that's going to be talking to your much bigger computer for whatever reason you'd like to be doing that. Oh, and by the way, the demo's in a week, and they've got investors there, and it has to work at least for the 20 minutes that the CEO is going to be on stage pressing the buttons that you are soldering today. So you better start quick. Now, the first blessing is that just from the niche that I'm in, most of the customers that reach out to me are already using Rust, or have already decided that Rust is what they would like to be using. So they're using Rust on a PC, on their microcontroller, on the phone, on the server, usually on both sides of this conversation that we're talking about today. And this makes everything so much easier because, surprisingly, you can share a lot of code from an itty-bitty microcontroller with 8 kilobytes of RAM with some hyperscaler server that's in the cloud, or the MacBook that you have that has 64 gigabytes of RAM on your desk in front of you. And the second blessing is we have serde. So you've probably used, if you've used Rust, you've probably run into serde somewhere. It's a library for serializing and deserializing data. But the special trick is that it doesn't just work on your desktops and servers, it also works on microcontrollers. Now, serde is about, I want to put Rust data on the wire. We are taking Rust data types that live in memory that the compiler put together for you very nicely, and we'd like to get it from here to over there. And that means putting it into some format that we can send over some kind of wire or radio. We have a type like this, an accelerometer reading. It has 3 fields, X, Y, and Z. They are signed. This is a Rust data type. It doesn't exist on the wire. But if we slap this on top of it, all of a sudden it goes on the wire, which is tremendously convenient. We've now solved the problem, but only halfway, because serde is actually split into 2 parts. The front end, which thinks about Rust data, and the other half, which is the data format. You might think of it as JSON or TOML or YAML or whatever format that you're using, but serde is the front end, and the data format crates are the back end. That's actually what we put on the wire. And whenever I say on the wire from now on, I mean Ethernet packets, serial ports, wireless radios, Wi-Fi, any of those things. That's the wire to me. Now, the problem is embedded systems don't always have nice things like operating systems or allocators. They are itty-bitty little friends who have so little. But luckily, Rust helps you handle this with no standard. It's a version of the compiler that lets you skip those things in the situations you need them for. Now, in 2019, there weren't very many data formats that worked with no standard. There were a couple. I didn't love any of them. So I came up with a crate called Postcard. Postcard is a library that is a data format that works with serde that's designed to work anywhere. Now, for one of the few times in my life that wasn't a customer project, I actually did the right thing and sat down and wrote down what I was supposed to be doing. What do I want this library to be? And lightly edited, it looks something like this. I had to remind myself that we are working for embedded systems first. It should run everywhere, but it should be specifically for embedded systems. It has to work no matter how small your chip is. 16 megahertz CPU with 8K of RAM should be no problem. And it should be as easy to use as serde as any other serde format. As easy as you slap serde JSON into a project and start slinging JSON over packets, it should be that easy no matter how small your chip is. And when you use it on your PC and on your microcontroller, it should be the same. It should not require special, painful, annoying code because I'm an embedded developer and I don't want to make my own job harder. And it has to be resource efficient. I've said we've got tiny little CPUs, tiny RAM, very little code size, and we have a lot to do as developers. That's a resource that needs to be managed. So I decided that these 5 in this order were how I was going to prioritize my work towards this. And like I said, I mentioned Wi-Fi, serial ports, all of these things. There was always going to be, embedded is full of, oh, well, we need it just a little different. It has to be a little special. So I knew that there was always going to have to be a little room for leverage there. So I made the format as dumb as I could, both because I'm not particularly creative, but also it makes it easier to deal with later. The format is probably about what you expect of, I have Rust data and I would like it to be in bytes. It probably works not very far from how you would sit down and come up with that right now in the next 5 minutes. It also doesn't do any bit packing trickery. It only deals with things at a byte level resolution. And this is because your desktop CPU might have some very clever instructions for doing very fancy things. That may not exist at all on the microcontroller, so you want to avoid anything that could cause serialization or deserialization to slow down to a crawl. And I come from a C background. I was taught C in university. You'd be surprised how many production systems out there, particularly embedded ones, just transmute structs or pointer casting in C from a struct to bytes, and then calling memcopy on those bytes, which you can do. You can do it well, but it's don't do it lightly. There's a lot of gotchas, and it will subtly break, and then you'll spend multiple weeks debugging it, like I did at multiple of my customers, which is a very frustrating experience that you were talking between an 8 and a 16-bit microcontroller, and it turns out endianness works differently sometimes. Now, Postcard is a non-self-describing format. That means it sends the raw values on the wire, nothing more. There's nothing about type names, nothing about field names, nothing like this. There are no safety rails. There is the data as it exists on the wire. Partially, this is for efficiency reasons. We don't want to be sending and receiving more than we have to, but also, why spend extra effort if your computer and your microcontroller agree on what these types are? Why repeat yourself over the wire? You're going to be spending way too much time sending data that's not actually useful to either side, usually. So because also I started this in 2019 and not 1974, where big endian computers are the standard, your microcontroller and your desktop and your server are probably all little endian machines, so we buck the standard network order trend of putting everything big endian, because why waste the extra cycles swapping everything on both sides? When it comes down to putting that data on the wire, it might work like you think. Structs, if you have fields A, B, and C, guess what order they go on the wire? A, B, and C. If you have tuples, they go 0, 1, 2. They just go in the order they are defined as the types. Slices get prefixed with their length, so you know how many things, and then they get serialized on the wire as you would if you were serializing just that one thing. Enums are prefixed by their discriminant, so you know I have this variant of the enum and the data that goes in that field. I told you it's been pretty obvious of how this design went. The one catch was originally slice lengths and discriminants were varants. If you've used gRPC or protobuf, variable size integers, or if you work in the compiler, LEB64 or something like that. We want integers to only take up as much space as they need because, for example, if you send a slice of things over the wire, how often are you sending 2 to the 32nd items? You're probably more sending 4 items most of the time. So why take up 4 bytes for that when 1 byte will do? Today, we've actually made all integers varants for portability reasons that I won't get into, but and I mentioned that need to customize down to the last little bit. I provided a system called flavors that are stackable combinators on serde. They work a lot like iterator chains. When you're receiving the bytes in and you want to deserialize them, it's kind of a hook point where you can modify those bytes before they do the deserialization. So if you have checksumming or compressing or some other encoding, you can do that while you're serializing and deserializing instead of having to do it as discrete steps. Usually this saves you some working memory as well. With all of these customizable flavors, I will tell you there are some generics involved, and generics are not always the most pleasant thing to have on your API surface, but for most of the common ones, we have helper functions that hide it, which means changing the entire way that the data is encoded is as simple as going postcard to slice, postcard to slice cobs, and now it is an entirely different wire format that helps you on serial ports tell where one packet starts and that packet ends. So 2019 to 2022, I used Postcard a lot. It was in a lot of my projects. And it turns out so did a lot of other people. It's become somewhat of a ubiquitous standard in the embedded Rust world to use Postcard because it works well for that domain. And about that time, I realized I was so worried about breaking changes and things like that it's time to make it 1.0. So for 1.0, I cleaned up the last portability issues that have to do with how serde deals with U sizes and I size and the fact that it doesn't tell you that it's doing that, which makes things not work so well on 32-bit and 64-bit processors. And I actually wrote a stable wire format, a document that's not coupled to serde or Rust in particular at all, that says this is how this data is encoded on the wire, because someday there might be something other than serde, or I might want to use a language other than Rust that uses this encoding. So 2022 and 2024, I kept using Postcard a lot. Ton of customer projects started popping up in even non-embedded places like Bevy or Wasmtime or let's see, there's some other ones, but people kept using it to shove stuff from memory into caches or on-disk file formats or blobs of data in their database and things like that because it just works pretty well and it goes pretty quick. I guarantee you if it works on that tiny little microcontroller, it's going to work on your server. It got to the point where basically every customer project I was doing, I was using Postcard somehow in one way or another. But I had a problem. And it turns out that if you have good tools that you like using, sometimes you use them too far. And you start using them for things that they're not really supposed to be used for, just because they're so pleasant to use. So let's look at that stack from my computer over a serial port or USB to something like that. We've got our physical layer. This is where electrons move back and forth or radio waves move back and forth. We're thinking in either bits or bytes, data on the wire, literally on the wire. Now, one layer up from that, we have to deal with framing. This is something where we turn either bits into bytes or bytes into frames, where we turn a stream of bytes into a stream of packets. If you're using Wi-Fi or UDP or USB, this comes as part of the protocol. You don't have to do anything. For serial ports, it's a stream of bytes forever. You've got to turn those into messages. This is where those flavors come in. Postcard lets you do that out of the box. The encoding layer is literally Postcard. It is encoding and decoding the data or serializing and deserializing the data. Great. And then I got to my customer projects where I had to write application logic. I had to actually make it do something because we're not just moving around these bytes for fun. We want to affect change from here to there. Now, like I said, Postcard handled all this stuff really well. You either had it out of the box, it gave you sort of like a polyfill to let you deal with that, and the encoding it had on lock. But this part for non-trivial projects actually was feeling less pleasant than I had wanted it to be. Particularly when you say, I'm not just sending one kind of data this way and another kind of data this way. I have a lot of different messages that I send back and forth, and I need to know how to deal with that. And it turns out that every project required a lot of custom work. It wasn't necessarily hard work, but tedious work. And as developers, we kind of hate repeated tedious work. You go, there's gotta be something better. And honestly, usually it was a lot of copy and pasting. I would have an open source project, and I'd copy that to the next open source project, or I'd take my most recent open source project and copy and paste that into a customer's project, because I had a rhythm down. It wasn't an abstraction because I was copying and pasting the same 3-4 files in different projects every single time. But I couldn't figure out how to abstract this. Every project was different. I had different behaviors. I didn't know how to make this consistent between them. And this part was hard until I realized that what this diagram was missing is a defined protocol layer. Because at the end of the day, Postcard is not a protocol crate. It's an encoding crate. And I had gotten complacent because I was so used to it filling in all those gaps around the communication that I had found that I kept using it for that. But it turns out I was using it beyond its means. Because the application is how these systems behave, your business logic, what they're supposed to do that's unique to that project. And a protocol is how these two systems communicate with each other. What behaviors do they expect from each other when it comes to passing data back and forth? And it turns out I was reinventing a bespoke protocol on every single project that I was doing. It was tremendously convenient and easy, but that was not really the best way to be conducting myself on these projects. And the really painful part is I had to do it every single time. Even very similar projects, I had to copy and paste the same chunk of code, getting bytes off the wire, framing it, deserializing it, figure out what to do with it, usually deserializing into a big enum coming in, match statement out, and then I respond, put it in a big enum going that way, and it was just kind of clunky and gross. But what if there was a protocol that was available out of the box, the same way that there's encoding or framing available out of the box? Because this part was easy because Postcard handled it for me. And if we had a protocol layer where someone's doing that work for me, or me yesterday is doing that work for me tomorrow, then that part becomes easy. This application layer stuff's still custom, but that's life. My customers are not all working on the same thing. My projects are not always on the same thing. That's always custom. It's going to be life. That's what I should get brought in to do. So meet Postcard RPC, which is a protocol on top of Postcard. So I said that a protocol layer is responsible for some behavior, some action, some way of communicating. So what ways of communicating does Postcard RPC have? Well, I've defined that you do have a client and a server role. And again, I'm not very innovative. A lot of these are going to sound very similar to other things that you've dealt with in your professional careers. Because when you define the roles like client and server, it makes other expectations more clear. You have your PC, and this is going to sound a little upside down to some people, but your big, giant 64 gigabytes of RAM PC is the client, and your itty-bitty little microcontroller is your server. Because if you think about it, your computer's asking your microcontroller to spin a motor for you, to read a sensor for you, to set the LEDs a certain way for you. So it's the server in this setup. Now, RPC is a term that means remote procedure call. You've probably heard of gRPC or JSON RPC. It's a common term in the industry, especially if you're talking with things over the network. And what this really means fundamentally is that we have a request and a response, and every request gets a response. The client initiates, the client asks. If you think about making a web request, you make a request to a server, and the server gives you back a response. It goes like this every single time, and they are always paired together, as long as nothing's gone wrong. And the reason why we call it a remote procedure call is because procedure is just a fancy name for a function, and you have a function that looks a lot like async function procedure that takes a request and gives a response. And you close your eyes and forget that there's a network in between these two, because when you model it as a black box, it just looks surprisingly like a function or a remote procedure call. The other behavior it has is topics or streaming and things like that. This is the kind of stuff you would use WebSockets for. Either I have a sensor that's pushing out data every 5 milliseconds, and I don't want to be asking for that data over and 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 over. You get the point. And doubling the amount of packets I have to send, you say just start sending the data. The word topic comes from, if anyone's used MQTT, it's a pub-sub-based protocol, and I just kind of stole the name because it made sense. Or the opposite, notifications. If you are waiting for a button to be pressed, you don't want to be asking every 10 milliseconds, is it pressed yet? Is it pressed yet? Is it pressed yet? You go, just tell me when the button has been pressed. And this doesn't fit into that RPC thing, so it turns out with these two primitives, you can cover a tremendous amount of functionality. Topics are also special because instead of just being initiated in one way and responded, they can go either direction. You can stream data to your microcontroller, or your microcontroller can stream data to you. But you never get to respond to these messages. It's a one-way broadcast. So, all like this or all like that. So, how does Postcard RPC do that? So, I said Postcard puts nothing extra on the wire. It just puts your data. So I've added one extra thing at the front. It gets a header with two different fields. The first is a sequence number. This is just a way of uniquely identifying what message this is, or this is the first or 10th or 10,000th message I've sent. And this is because our microcontrollers, like your big servers, sometimes take different times to process different requests. If I say, start spinning up the motor and let me know when it hits this RPM, that might take longer than, what's your version number? So we give it a unique ID, every way going that way, so we know which response goes with which request. And the other thing they get is a unique key. And this is a way of identifying what kind of message it is. So I've mentioned Postcard, again, does not send anything about schemas and things like that. It sees bag of bytes and tries to deserialize it to the type you tell it. But that doesn't help us if we are sending it a lot of different types of data. So the way that we do this is we take a path or the URI or the endpoint that we're talking about, and we hash that, and then we hash the schema of a message. We actually, at compile time, have a proc macro schema that expands to the schema of the message on the wire, hashes that, including all the fields and types and things like that, and combined with the path, you get a unique key that uniquely represents that request or that response. For now, keys are 8 bytes, but this is just because it was big enough to avoid collisions for me and not too big to be extra overhead. And these keys are generated at compile time because it'd be very silly to be doing this hashing at runtime. So I wrote a compile or const function that can do fnv1a hashing. So you just do this once, the compiler saves it, and it's just a bag of 8 bytes that you throw at the top of every message. And now that the protocol is standard, we can begin providing reusable protocol code. On the host side with USB, we've got a lovely crate called NUSB that exposes the low-layer guts of USB in a handy async format. And on the embedded side, we've got a crate like Embassy USB, which is a USB stack that works on basically any microcontroller with USB, whether it's from STM or Nordic or Raspberry Pi. So in this stack, now I can give you a library for that host client, and I can give you a library for that target server, which means now I've cut all of that boilerplate out, and you just have to worry about your application up there. So what does the code look like? Well, something that I did before, but I've continued doing, is when you've got your microcontroller project, that's a binary crate, and you've got your desktop project, that's a binary crate, they need to share what kind of types they're going to be sending back and forth. So you usually have a crate that has nothing but data types in it. Normal sort of looking stuff, derive, serialize, deserialize, that extra schema derive that's on there, not a lot of extra work. So you might say, I'm going to tell you to go to sleep for a certain amount of time. And then I'm going to expect you to respond back to me exactly how long you slept, because maybe you slept a little less, a little bit more. So we have this endpoint macro that says we're going to define the sleep endpoint with the request of sleep, the response of sleep done, and the path is this sleep. The reason why we have this path there is because you might, especially for common types like integers or whatever, you might have a bunch of endpoints that give an integer and get back an integer, so we need a way of uniquely telling the difference between them. We just hash it, so it looks a lot like paths or URIs or endpoints on web requests, but it's just going for style. Now, what that macro does is it generates that struct and it fills out this trait implementation. I don't have a good name for this. Maybe a lot of smart Rust people in the room. I've just been calling these metadata traits. It's a convenient way of coupling types and consts together. So this endpoint has a specific request type, a response type, the path value, and then at const time, we generate those keys. So that's all that macro does, and it just bundles them into one name because they always travel together. Similarly for topics, for those broadcasting things, We have a type, serialized, deserialized schema. We declare a topic, same kind of thing. We get a trait, this metadata trait that has a type and some consts on it. So on the embedded side, instead of having to write a lot of code for serializing, deserializing, basically doing all the plumbing that we have to do, instead, we can just write these function handlers. And if you've used Rocket or other web crates like this is going to look a lot like those endpoint handlers you write in those crates. You have a function that takes some context. We get the header that we were talking about and the request. So this first one describes a request that takes nothing and gives back a U64. The second one's an async function that gets a single lead struct and gives back some kind of result. We also have the ability to say, we're going to spawn a whole task just to handle this, because maybe that one's going to take a while, so we don't want to wait for that answer to be ready before we go on to process more information. And then at the top of our microcontroller code, we can define the routing or dispatching in one place in our code. This is a big macro, don't worry about it, but because we're working with a lot of different chips that have different USB drivers, some of them are single core, some of them are multi-core, this is just some details you need to tell us how to handle that. And then you get this little match statement looking block that just says, when you get this endpoint request, call that function. This one, that function. This one, that function. Instead of like a proc macro like you would in Rocket, we just put all the routing in one place. And you'll notice that there's different flavors of them: blocking, async, or spawn. And that's, do we call a blocking function an async function, or do we spawn a whole async task to handle this? And because all of these endpoints have the types associated with them, we can generate all the code for the requests and response because we know the types at compile time. And on the PC side, you don't have to write your own plumbing code either. You can make an endpoint request that looks like this. You connect to some device with the product stream OV-twin, and then this is all it takes to send a response over raw USB, have it be serialized, have it go to your microcontroller, wait for your microcontroller to respond, deserialize the response, and see if it went well. Send, and wait for the response. And you give it that ping endpoint because that's all the data it needs to know exactly what kind of types over the wire we're going to use. Same, if you were on the desktop and you want to subscribe to that stream of sensor data, we've got a method for that. We've got client.subscribe. You give it that topic metadata, and it goes, I know exactly what I'm going to be listening for. You tell it buffer up to 8 items, and it gives you an interface that looks like a Tokyo channel, basically. You can just await receiving the next message, and you'll get it every time it comes in. So we've separated our concerns. We now have the ability to not specify this in every project, provide reusable code on both sides, and to make having that whole conversation just as easy as serializing and deserializing the data was. Because Postcard is about making data go from here to there effortless, and Postcard RPC is about having that conversation be as effortless as possible. Because no matter how you connect to your device, whether it's USB, serial port, Ethernet, whatever, they're never more than a postcard away. Thank you.
That was a very nice presentation. Thank you very much. And I'm sure there are questions. Who wants to go first? I see a hand there over there.
Thanks for your talk. Given that you just encode stuff in order of the properties, how do you handle changing your structures and then deploying them one at a time on both ends?
You don't. Yeah, that's a very good question, and that's one of those things that schema evolution is one of those challenges that I've faced over time, particularly because firmware devices get updated on a way different scale than servers or desktop applications do. Postcard RPC takes the most conservative choice here. You change anything about that struct, the name of the field, the ordering, things like that, that hash changes, which means then if you make that request with the wrong data type, it says, I have no idea what you're talking about, because it just knows that hash value there. So it doesn't help you with that, but it does help you from the foot gun that you might misinterpret that message. And my opinion on that is generally that if you have a desktop or a server, have all versions of the packet and figure out which one you should be using, and have maybe one version ID that never changes, but it will never misunderstand that. At least in Postcard RPC. Postcard, you just don't, or otherwise it might have problems. Yep.
Next question is over there.
I was wondering how configurable this crate is. For example, I have an application I do with students where using these sequence numbers and sending back responses is just something we don't want and don't want to pay for. Can you strip parts out of this, or are you getting the full package always?
Right now, Postcard RPC is very opinionated. It says you get the sequence number, you get the header. You can take the vibes of this and customize it as you like. Not going to bug me. Want to avoid the ability, especially in embedded, we had the habit of making everything tunable, which made the UX horrific because you got 9 generic parameters and you've got a compile time feature. So the answer is no. As I go on, I will probably eventually hope to formalize this protocol the same way that I did the wire format of that and sort of make it more specified. And for there, feel free to take the ideas and run with it. But for now, I'm saying this is any color you want as long as it's black, kind of.
There you go.
Yeah, so thank you, James, for a great talk. You kind of mentioned that Postcard RPC could fit in the same place as MQTT, right? So what if I wanted to talk to a Postcard RPC broker, if that's your term, from an application that's written on Sever, for instance?
Yeah, right now, again, generally you can't. It relies real hard on serde for the encoding information. Excuse me. You could always FFI and things like that. But as I mentioned, I'm primarily focused on Rust to Rust communication today. Like I said, I hope that Postcard will outlive serde and that it could use whatever is different than that. Or there's certainly cases where I would love to have a code gen tool for C or Python or C# and things like that. Because not all of my customers use Rust for all of their parts of their entire stack. So the answer is, if this proves itself out well and I learn from this and it goes fairly well, I'm interested in that. But also I need to be careful not to overstep because Postcard RPC also does not handle addressing and things like that. It assumes either you have point-to-point or you're handling that. So maybe the next step is Postcard NetStack, I guess. But MQTT has quite a few components in it for both routing and communication and things like that, or ignoring it because it's pub sub and you have a broker that you're talking to. So the answer is you could probably build something in that shape, particularly those two primitives of endpoints and topics composed together really well. Like sometimes you have an endpoint to start streaming on a topic or an endpoint to stop streaming on a topic and things like that. So maybe, but also it's more peer-to-peer than broadcast right now. But that's interesting and I'd love to talk to about it.
Thank you.
Got a question over there? I will want to know about your step counter later.
Hi, so I was wondering, does the prop macro check if the key is unique over the entire application? Or can you accidentally, by specifying the same path and the same type, get a collision?
So it's a declarative macro, not a proc macro. But I can tell you that define dispatch macro, this this essentially just boils down into a big match statement of the 8 bytes on there. And I put in the expanded code deny unreachable match arms. So if you either accidentally put the same endpoint twice or somehow get a hash collision on one of these, it won't compile unless you disable the deny. But I have deny unreachable match arms, so you'll get a compile error, at least in this implementation of it today. Yeah, and that's part of the reason why I want to have that whole thing in one blob, is because it gives you that sort of whole program visibility to say, these are the endpoints that I'm talking about. So you only catch it when you build your server, but your server will refuse to have totally masked away endpoints.
All right. Any other questions? Oh, over there. Ooh. Eager arms going up.
Thank you for the talk. My question is quite short. Is it canonical format, like how it serializes hash maps?
Sorry, can you repeat that?
How, will two different PCs with two different programs running in RAM with the same keys, hash map produce the same binary, or it depends on the seed?
Yeah, it's deterministic. It uses specifically FNV1A, and the way that I do it is essentially, it's deterministic. So whether you're compiling for a microcontroller or whatever, that hashing that gives you the key is totally deterministic, because it basically recurses through the schema in a specific way, and it hashes the text in a certain way. So it is deterministic. Does that answer your question? Cool.
Okay. Thanks. I have a question. In your stack, you have Postcard as the wire format. Then you have a Postcard RPC for procedures. But what do you use for frames, basically? When you have a TCP stream or like Bluetooth stream, how do you distinguish bytes into messages?
Yeah, so Postcard itself has a flavor called COBS, which is a secret weapon from the days of dial-up. And it's a neat trick of you use zeros or null bytes as the frame delimiter, and it's a way of encoding messages so that none of the data bytes are zero. So even if you were to send a packet full of zeros, what it does is it essentially makes a linked list between all the zeros in the message that terminates at the frame header, and it's tremendously performant, and it's, like I said, it's from like the days of telephone network framing. It's called COBS, consistent overhead byte stuffing. So Postcard has that as a flavor. I have one variant for USB. We don't need that because USB has its own built-in framing. But I do have a version of Postcard RPC that works over UARTs, like raw serial ports. So it uses Tokyo serial, puts COBS framing in front of that, and then on the other side. I don't have the pretty server macro working on anything but USB right now, but that's just a limitation of what I've coded so far. So COBS is my go-to answer, but there's a lot of other ways to do it. But COBS is my favorite because it's fairly efficient, resilient, and with very little overhead, and not a lot of room to mess up. So I really like it. And Postcard has a ton of helper functions and structs and types that help you do COBS with Postcard, because everyone who's using it over a UART or USB serial is basically using COBS with Postcard.
All right. Final question. Nobody else? Yeah. Final question. There we go.
I'll be here for all of tomorrow and through the Impl days or the Unconf if you'll be here. So definitely feel free to come grab me.
So I use Postcard for serializing data for Deoxys, and Postcard doesn't support all tags of serde. So I'm wondering if you think those more tags would be possible to support for Postcard, or if it is something that a public library that uses serde should keep in mind when deriving the data format.
Yeah, so there's a number of, serde has its own customization fields. If you've ever used like serde flatten or serde rename and things like that, the way that serde is implemented, it doesn't bring all of that information down to non-self-describing formats. It sort of just confuses the serializer and deserializer. I have an open issue on the serde repo asking how to handle this, but my answer, unfortunately, is just don't use those. And that sometimes is painful when you have something that's like taking JSON messages in and you want to then turn around and reserialize that as Postcard and the other way out. And unfortunately, right now, the only answer I have is to duplicate those types without those, which is really unsatisfying. But I have an open issue because it does bite people sometimes when you use flatten or other attributes like that. And unfortunately, I haven't gotten a response back of how to handle that as a data format writer. So I'd love for there to be one, but I have a feeling it'd probably end up having to be a breaking change to serde, which I don't know when or if would happen. Yeah, thank you. It's definitely a common pain point, and I've had other people run into that too.
All right. Thank you very much.
Thank you.
Thank
you so much.
you.